discussed the moments, so the mean, the variance, then the third moment and the fourth central moment, and the measures of skewness and what is the explanation for that I had given, and the measure of kurtosis. So you are clear up to that point? Do you have any questions on that? Anybody who is having any questions on that till that point? Nobody has a question? Hello, can you hear me?
Yes, sir.
Yes, sir.
Okay. If you have no questions, then I will proceed. So we look at the moment generating function of the binomial distribution. It is expectation of e to the power tx, and so that is equal to summation e to the power tk n ck p to the power k q to the power n minus k. So this is equal to so this term n ck, and then this term I will combine here, p e to the power t to the power k q to the power n minus k, k equal to 0 to n. So this becomes nothing but the binomial expansion of q plus p e to the power t whole to the power n. So this is the moment generating function of the binomial distribution. Okay. Is this calculation clear to everyone?
Yes, sir.
Yes.
Okay, so let me take one example for application of a binomial distribution. So the question is like this, that if there are 50 seats on a flight, the airline actually sells little more than 50 tickets. It sells 52 tickets, assuming that 5% of the persons do not eventually turn up. So they sell little more so that the flight doesn't go vacant. So what is the probability that every passenger who turns up will get a seat? Now this is a problem which is there in major airlines. It happens, I mean, in American Airlines, United Airline, and so on. Many times you might have read in the news that some celebrity, he went to catch the flight and he was denied the seat, and then there was a hue and cry. So it happens many times. So this problem is related to application of that thing only. Let us see what is the probability, how often it may happen. So let us say, let me define X as the number of passengers number of passengers who turn up for the flight. Then you know that the chance that he does not turn up is 0.05, because 5% of the people do not turn up. So then we can say that X follows binomial distribution, and since 52 tickets are sold, so N is 52, and the probability that he will turn up is 0.95. So this becomes a binomial distribution. So what is required? That he gets the seat. So that means we are asking what is the probability that the number of persons who turn up is less than or equal to 50. So this is becoming an application of a binomial distribution straightforwardly. So you can see this is equal to 1 minus probability X is equal to 51 and X is equal to 52. So we will put it in 1 minus mode so that the calculations are simple. So this becomes 1 minus 52 C 51 0.95 to the power 51 into 0.05 and 0.95 to the power 52. So you can evaluate it easily, and this is approximately 0.74. So roughly you can say that the chance that a random passenger he will get a seat is 0.75. That means there is a chance that, I mean, in fact, the chance is little more than 25% that he may not get a seat, and that is why you hear such news items that somebody went to and he could not get a seat, and then there was a big hue and cry and so on. In railways, they will sell exactly the number of seats that are there, and that is why you find many times that the seats are vacant because they do not oversell. But in airlines, generally the practice is to oversell. Is this problem and its solution clear to you?
Yes, sir.
Okay, let me move to another distribution. So we talk about geometric distribution. Okay, in binomial distribution, we are having a certain number of trials, and the random variable is how many success are there. That is the random variable. Now let us look at it in a reverse way. So suppose you take a test, maybe some entrance test for something, and then you want to see whether you qualified or not. So suppose you don't qualify, then you appear again, isn't it? And then you see whether you will qualify or not. Similarly, suppose there are trials for certain, like vaccine trials. So you see that it is given to somebody, and whether it is successful or not, then another trial is conducted whether it is successful or not. It is conducted till it becomes successful. So here the number of trials is not fixed in advance, rather that becomes a random variable. What is the number of trials needed for the first success? So it is like something like in a game of Ludo, where you throw the dice till you get a 6, so that you can start your movement of your piece, isn't it? So here the Bernoullian trials are conducted, but the random variable has been changed compared to the binomial distribution. So suppose Bernoullian trials are conducted till the first success is achieved. So let x denote the number of trials So what are the possible values of x? X can take first one, that means there can be a success in the first trial, there can be a success in the second trial, and so on. But you cannot end here. So it is it is countably infinite number of possible values that the random variable can take. So what is the probability that x is equal to, say, k? That means what is the probability that the first success occurs on the kth trial? Then it means that, see, suppose we are considering this as the trials, then these are all failures and the success occurs on the kth trial. Okay, so you have k minus 1 failures here. So q to the power k minus 1 into p, because we are assuming the trials are conducted independently, so the probabilities will be simply multiplied, k equal to 1, 2 and so on. So this is the form of the probability distribution. It is called geometric distribution. Okay. Of course, you can see that the sum is sum of this pxk, k equal to 1 to infinity, that is sigma k equal to 1 to infinity q to the power k minus 1 p. So this is nothing but, see, what are the terms here? P plus pq plus pq square and so on. So this is nothing but p into 1 plus q square, that is the infinite geometric series, and the sum is 1 by 1 minus q, so this becomes 1. So the sum of all the probabilities is 1. So this is a valid probability distribution. So the name geometric distribution has been given because actually you encounter the geometric progression here as a sequence of the probabilities, and therefore the name is given as the geometric distribution. Let us look at the moment calculations here. Say, for example, what is the mean of this distribution? So k q to the power k minus 1 p. So if you look at this here, what are the kind of terms that you are getting? The first term is p plus 2pq plus 3pq square and so on. And if you and if you are taking out p here, then the series that you are getting inside the parenthesis, it is nothing but arithmetico-geometric progression that you know, and the sum is, what is the sum? Can anybody tell me? It is 1 minus q to the power minus 2. So it comes in the denominator. So it becomes 1 by p. Are you familiar with this sum?
Yes, sir. Yes, sir.
Now you try to look at the interpretation of this one. See, we are saying that in the Bernalian trial, the probability of success is P. Then what is the number of trials, expected number of trials needed to get the first success? So it is 1 by P. So in the dice tossing problem, see, if we are looking at the fair dice, then what is the expected number of trials needed for the first time you get a 6? So on the average you expect 6 times. Similarly, if you consider a coin tossing problem and you are considering a fair coin, what is the expected number of trials to get the first time head? So expected number is 2. Of course, you can get in the first one also, but the expectation is 2 here. Of course, it can be 2, it can be 7, it can be 9, and so on in the first trial in which you get, but the mean is 2. So that is the interpretation. Now you see, if I am calculating the higher order moments, then in the next one I will get P into 1 plus 2 square q plus 3 square q q square and so on. So you can see, I mean, these are higher order arithmetico-geometric progressions. So we can use some formula actually for calculating expectation of x into x minus 1. Again, like in the binomial, you have to consider the factorial moments first. So we can use, I am just writing down the formula. Of course, I think all of you are familiar with this formula because in your class 11, 12, you have done this arithmetico-geometric progressions, etc. So the formula can be written like this. That is sigma, say jck r to the power j minus k, where j is equal to k to infinity, or we can write like this also, k plus I c k r to the power I is equal to 0 to infinity. This is 1 by 1 minus r to the power k plus 1, where of course r is less than 1. Are you, some of you are familiar with this formula? Are you familiar with this formula?
No, sir.
No. So anyway, you can note it down and you can try to prove it yourself. I mean, this is not something which is very difficult. So I will put it as a star. Okay. So prove it yourself.
Sir, could you please scroll up a little bit?
Huh?
Yes, thank you, sir.
So we can use this for calculating the higher order moments, and then you can, so let me just write, for example, mu2 prime. Mu2 prime then will become 1 plus q divided by p square, and therefore the variance that you can calculate, variance of x becomes mu2 prime minus mu1 prime square, that is becoming q by p square. So the variance of a geometric distribution is q by p square. Actually, I am not calculating here the third one and fourth one because the form of the distribution is such that you can easily make out what is the shape of the distribution. For example, the first probability that you are having is p. Then second one is qp. Now q is a number between 0 and 1. So it will become less than p. So it will reduce. Then the next one is q square p. So it will further reduce. So if we are considering this distribution, it will be like this. Okay, it will be reducing. Of course, the amount of the slope will be dependent upon what is the value of q. So for example, if p is say 1 by 10, then q is 9 by 10. So the decline will be slow. But if I say p is equal to say half and q is half, then every time it will become half of what is the previous number. So it will become like this one, then next one will be like this, and then so it will decrease very rapidly. Okay, so in all the cases, whatever be the thing, it is always positively skewed. So I am not actually looking at the third moment and so on, because you can immediately make out from here. Let us look at the moment generating function of geometric distribution. Okay, so from here itself it suggests that you will combine this e to the power tk term with q to the power. So we can write it as p e to the power t sigma k equal to 1 to infinity and q e to the power t to the power k minus 1. So it is same type of geometric series. Only thing is that the common difference, common ratio is now q e to the power t. Now you know that if you are adding the infinite geometric series a plus ar plus ar square and so on, what is the condition? That r should be between -1 to 1. So here q e to the power t, because of course here it is positive, so there is no question of negative, but it should be less than 1. So then this can be summed up and you get the sum as p e to the power t divided by 1 minus q e to the power t. So it is this, if q e to the power t, so let me write here q e to the power t is less than 1, which implies that basically t is less than minus log of q. So moment generating function exists. So you may not get confused here. Log q is actually a negative number because q is a probability. So it will be between 0 and 1, and therefore log of q is negative. So minus log q is positive. So this is fine. It is not a problem here that you are having here. Let me give one exercise here. Suppose independent tests are conducted on mice while developing a vaccine. If the probability of success is 0.2 in each trial, what is the probability that at least 5 trials are needed to get the first success? So here, if I am looking at the x as the number of trials, needed to get the first success, then x follows geometric distribution with probability of success 1 by 5. Now, what is the question asked? What is the probability that you need at least 5 trials? So that is k equal to 5 to infinity 4 by 5 to the power k minus 1 by 5, because p is equal to 1 by 5. Again, it is directly the geometric sum. Only thing is you have to adjust the terms here, because the first term is 4 by 5 to the power 4 into 1 by 5, and thereafter you are having this sum. So this is nothing but 4 by 5 to the power 4, 1 by 5, 1 divided by 1 minus 4 by 5. So it is nothing but 4 by 5 to the power 4. Which is nothing but 0.4096. So roughly you can say 40% chance is there that you will get the first success on a trial not before 4th trial. That means on a trial beyond 5th trial. Is this problem and the solution clear?
Yes, sir.
Yes.
Now let me just take up one property of this distribution here. So let us look at this. So if I am saying x follows geometric distribution with probability p, what is the probability that x is greater than m? In the previous problem I have calculated x greater than or equal to 5, isn't it? So here I am asking what is the probability x greater than m? So greater than m means that till m trials the success has not been observed. Okay, so that means the success starts from the m plus 1th trial onwards, q to the power k minus 1 p. So what are the type of terms that you are getting? Q to the power m p plus q to the power m plus 1 p and so on. So this is nothing but q to the power mp 1 plus q square and so on. So that is q to the power m p divided by 1 minus q, that is q to the power m. So what I have calculated, in a geometric distribution, what is the probability that the success has not been observed till m trials is q to the power m. Okay, if the probability of success is p, then the probability that the first success has not been achieved till mth trial is q to the power m. That means you can also say it like this: the weighting, the number of trials for weighting is at least m. In fact, it is at least m plus 1. That means till m you have not achieved. The probability is 1 minus p to the power m. Now let me look at another probability. So what is the probability that the success has not been achieved in m plus n trials, given that the success has not been achieved in n trials? So that means in up to n trials the success was not there. What is the probability that even after another m trials you will not get the success? Okay,
q to the power
okay.
m.
So we apply this. Yeah, it was the previous one was q to the power m. Yes. So now let us consider this as events a and b. Then what is the formula for probability of a given b? It is probability of a intersection b divided by probability of b. So this is becoming probability of a intersection b, that is x greater than m plus n intersection x greater than n. So that is probability x greater than m plus n, because a becomes a subset of b, and in the denominator you have probability x greater than n. Now already we have developed the formula, so it is becoming q to the power m plus n divided by q to the power n, that is q to the power m, which is nothing but probability of x greater than m. What does it mean? If it means that starting from the first trial, if we say that the success has not been achieved till m trials, the probability of that is not dependent upon where you start. So even if I start on the nth trial, the probability of not getting a success till the next m trials is same irrespective of the starting value of n. N can be 1, n can be 10. This is known as the memoryless property of the geometric distribution. So for example, some of you might have bought an old calculator or old cycle from your senior, and when you bought it, it is in the working condition. So the probability of its failure, I mean, rather than you can say not failing till another, say you are here for 5 years or 4 years, so not failing till that time, it remains the same irrespective of the time that it has been already in the use. Of course, we assume that the failure rate of this type of thing is geometric distribution. Okay, so geometric distribution models are helpful in the robust models, where the robust instruments or robust equipments are there, where things do not change that rapidly. Okay. Is this memoryless property and its interpretation clear?
Yes, sir.
Is the
Yes.
interpretation of it is clear? Yeah, okay. Now, in place of the first success, suppose we are looking at, say, third success or 10th success. Now it is like this, that we are considering, say, selection of candidates. Okay, so certain trials are being conducted, and first time, so suppose I need 5 people, so as soon as I get the 5 people, I stop the trials. Okay. Similar thing may happen in some other kind of selection procedure where we have to select the people. So once our selection pool is over, then we stop the trials. So in place of the first success, we look at rth success. So again, so this distribution is now of course known as negative binomial distribution. Let me write the name first. So suppose until the rth success is achieved. So until the rth success is observed. Okay. So if I am putting x as the number of trials needed for rth success, then x can take values r plus 1, because at least r trials will be needed to get the r success, and it can be r plus 1, r plus 2, and so on. Okay, so these are the, again it is an infinite valued distribution here. The number of values are countably infinite. How to calculate the probability distribution of probability mass function of this, that is, what is the probability that x equal to k. So you can just look at this. Suppose these are the trials here. Okay, here if I am saying this is the kth one, then this one should be a success, last one should be a success. Before that, in k minus 1 trials, I should have r minus 1 success. So that is why this last one, if it becomes success, then this will become rth success. So that means in the previous k minus 1 trials, you have r minus 1 success, and the probability of that is p to the power r minus 1 and q to the power k minus r. And the last one is a success. So again you multiply by p. So this p and p to the power r minus 1 can be combined. So I can write it like this, p to the power r here. Okay. So here k is equal to r plus 1 and so on. You compare or contrast it with the binomial distribution. In the binomial distribution, the number of success is fixed, and you are looking at the number of in the binomial distribution, the number of trials is fixed. You are fixing n as the number of trials, and you are making the random variable as that what is the number of success, that is the random variable. In negative binomial distribution, the number of success is fixed here, that you are saying I need r success, and how many trials for that will be needed, that is the random variable. So it is a something like a different way or negative way of looking at the binomial distribution, or inverse way of looking. So that is why this distribution is known as negative binomial distribution or inverse binomial distribution, etc. These are the names that are given for this. Again, you can see if I am looking at the sums here, for example, if I want to sum this one, then I have to use the same formula which I wrote earlier. This formula that I have written here for calculation of the moments, this red starred formula, that sigma j c k r to the power j minus k, j equal to k to infinity, that is 1 minus r to the power minus of k plus 1. So this same formula will be utilized for finding out the sum of negative binomial distribution or calculation of the moments, etc. So I will not be doing the calculations here. Let me just write it here. So mu1 prime is expectation of x. This will become r by p. Again, the interpretation you can see. What was the number of expected number of trials to get the first success? It was 1 by p. So what is the expected number of trials to get the r success? It will become r by p, because for each of them you need that many number of trials. So expected number of trials is nothing but the sum here. And in a similar way, mu2, that is the variance of x, that becomes rq by p square. I will not be getting into the higher order moments, etc. Let me put this as for you to check all these things. Okay, you just try to work out. I mean, this is of course very simple calculation because I have already written the formula. So you have to just apply that thing. What is the moment generating function here? So that is e to the power tk k minus 1 c r minus 1 q to the power k minus r p to the power r and k equal to r to infinity. So the way we want to combine, we just combine this term e to the power tk with this one q to the power k minus r. So if you do that combining, this becomes p e to the power t divided by 1 minus q e to the power t whole to the power r. And again the condition is the same, that t is less than minus log of q. Okay. So we look at one example here. Suppose an airplane fails if two of its engines fail, and the probability of failure of each engine is say p. So if I say x is the number of engines failing, then what is the probability distribution? It is nothing but the negative binomial distribution. R is here 2. So 2 minus 1 q to the power k minus 2 p square, which of course you can write it as simply k minus 1 q to the power k minus 2 p square, k equal to 2, 3 and so on. Okay, so I mean, this is a direct application because you know that in nowadays large aircrafts are there. So generally they are four engine. This Boeing or Airbus, they are four engine planes. So they fail if two of them fail. Of course, now they have made a six engine plane for very long haul flights like this Bangalore to San Francisco and all. So they are having six uh, engines, and of course the system will fail if three or four of the engines fail. So it is something like that. So is this negative binomial distribution and its application clear to you?
Yes, sir.
Yes, sir.
Okay, so let us just have a break for 5 minutes, and then we start again. I will start for another distribution, new distribution. So far we are looking at the trials in which they are conducted independently under identical conditions, and the probability of success is considered to be the constant. So basically by success we mean that there are two types of outcomes, one of them which we call success and the other one we call failure. But there are other situations where we do not have this independence and identical kind of thing. Rather, we are looking at a experiment in a restricted mode. So, for example, you have two types of people. So, for example, in my class, there are boys and the girls, or there are students who are of two different branches or two different, say, for example, the students who are in the 4-year programs and then the students who are in the 5-year programs. So, a similar thing happens in a population, for example, when we are doing a survey on a disease. So, there are people who are infected with the disease and then there are people who are not infected with the disease. The people who are cured with it from a treatment, the people who are not getting the cure from a treatment are so this kind of situations is slightly different from the experiment that I have studied or described till now, in the sense that uh, in the previous case, every time the probability or the experimental conditions are remain the same. But when we are looking at a finite number of things, then it is not the same. So the situation is changing, and this in this case the description is by another distribution. It is known as hypergeometric distribution. So the setup is like this. I have suppose a population has n elements, okay, and so it is something like a big basket. So there are n elements here, but out of this n elements, there are m elements which are of one type and n minus m elements which are of another type. So we can call it type 1 and type 2. I mean, it is again, the description is similar to the success failure kind of thing. But here, when we do the selection, the probability will change every time. So for example, if I select one item, what is the probability that it is type 1 item? The probability will be m by n. But now after the first selection, if I am looking at the second selection, then what is the probability of the second item also being of type 1? Then it will be dependent upon the first one. So the probability will get modified. Okay, so we say that suppose n items or n elements are selected at random. Without replacement. So we write it as WOR. And X is the number of items of type 1 in the selected sample. Then what is the probability that X is equal to K? So from total n number of items, we are choosing a small n number of items. So the number of possibilities is NCN. But now out of the capital M one type of item, I am selecting type 1 item K. So MCK. Then remaining items are from type 2, that is N minus MC, N minus K. So what are the possible values of k here? K can take value 0, 1 to n, and of course subject to the condition, because this k should be less than or equal to m, and n minus k should be less than or equal to n minus m. So you can say that basically k is less than or equal to m, and n minus k is less than or equal to n minus m. These two conditions have to be met, otherwise this notation will become invalid. So is this probability clear to everyone?
Sir, can you explain this part once again?
So we are having capital N number of items, and we are selecting a small n number of items from there. From capital N item, you have two types of items. So capital M items are of type 1 and n minus m items are of type 2. So if we are selecting a small n number of items, out of that, how many are of type 1? That we call as the random variable x. So what is the probability that you have selected k number of items which are of type 1? So total number of ways of selecting a small n number of items from capital N is NCN. Now out of that, small k items are from type 1. So that is MCK, because M is the number of type 1 items, and remaining n minus k items will be of type 2. So that is n minus MC, n minus k. So this is a basic property of the combinations which you have studied even in, I think, your class 12, 11, 12, when you had the permutations and combinations. So is it clear to you?
Yes, sir.
Yes, sir.
Okay. To say that this sum must be 1, you can use this simple identity here, that 1 plus x to the power n is equal to 1 plus x to the power m into 1 plus x to the power n minus m. So if we look at the coefficient of x to the power n on both sides, we get NCN is equal to sigma MCK n minus MC n minus k equal to 0 to n. So it is a valid probability distribution. So this is known as hypergeometric distribution, and for calculation of the moments etc., you have to proceed in the same way as in the binomial distribution. In the binomial distribution, what did you do? You adjusted the product term with the factorials. So the same thing will be done here also. You have okay, so if I multiply this by k here, then that k you have to adjust with this k here. That is MC k. If you expand, you get m factorial divided by k factorial into m minus k factorial. So one k factorial term, one term you will cancel out, and then you will adjust with a smaller order of the factorials. So if I calculate, say, mu1 prime, that is sigma k mck n minus mc n minus k divided by ncn, k equal to 0 to n. So you can easily see that the first term is gone here. This k equal to 0, if you put here, this is 0. So I can put it here corresponding to k equal to 1 now. In place of 0, I can put here 1. And then this term you will adjust here, k, then m factorial divided by k minus, well, k factorial, and then I will write it as m minus k factorial, and then you have this n minus m factorial divided by n minus k factorial n minus m minus n minus k factorial divided by ncn. So k equal to 1 to n, and this k and k factorial I will adjust here. So I will put it as k minus 1 factorial here. Now this immediately suggests that we should adjust this k minus 1 here, because I will put k minus 1 as say j. So if I put k minus 1 is equal to j, then this is j is equal to 0 to n minus 1. So you can see that everything has been reduced by 1. So then I adjust those terms. I will take one m outside here, then one n has to be taken from here also, and then one k will come out. So sorry, one m, then n, and then a small n will also come out, because one term will come out from here. So let me put it like that. N m by n, and then you are having all these terms coming. That is j is equal to 0 to n minus 1, m minus 1 cj. This will become n minus 1 minus m minus 1 c n minus 1 minus j divided by n minus 1 c n minus 1. So you can see this is again a hypergeometric distribution, everything reduced by 1. That is the total population size is n minus 1. The number of items of type 1 is m minus 1. The number of items of type 2 will remain n minus m, which I of course I have written as n minus 1 minus m minus 1 here. And therefore this sum is going to be 1. So this is nothing but n m by n. If you leave aside the little bit of complicacy in the calculations, you can understand one thing. You are having number of items of type 1 as m out of the total population size n. So what is the proportion of type 1 items? It is m by n. So if you are selecting n number of items, what is the expected number of items of type 1? It is n into the proportion, that is capital M by capital N. So physically, if you look at it, is very simple to understand. Of course, I have shown you the complex mathematical calculations here. Now that calculations will help you to calculate higher order moments also. So for example, if I want to calculate expectation of x square, then I should firstly check expectation of x into x minus 1, like in the binomial case, and so on. So without doing these calculations here, I will write down the expressions. So you can see that you will get expectation of x into x minus 1. So if you keep the analogy with the previous one, you will actually get it as n into n minus 1, because you have to take out two terms there, into m minus 1 divided by n into n minus 1. So using that, you can calculate expectation of x square, that is expectation of x into x minus 1 plus expectation of x. So after simplification, you will get the value that is n m into n m minus m minus n plus n divided by n into n minus 1. So this you can use to calculate the variance of x. So that is equal to n minus small n by n minus 1 n m by n 1 minus m by n. See, one thing you should note here, suppose I consider both m and n tend to infinity such that m by n tends to some number p. Then the expectation converges to small np and the variance will converge to npq, that is np into 1 minus p, which is the same as in the binomial distribution. That means if the population size is very large, then this hypergeometric distribution actually converges to binomial distribution. Okay, I will state it as a theorem here. Let x follow hypergeometric distribution with parameters m, n and n. What are the meaning of parameters? You had population size capital N, m is the number of items of type 1 and n is the sample size. Then as if m tends to infinity, n tends to infinity such that m by n tends to p, then pxk converges to nck p to the power k q to the power n minus k. So I'm leaving it as a do it yourself exercise. Okay. Of course, the applications of hypergeometric distributions are obvious because as I mentioned to you that in finite population sampling, this is always applicable. Like if I have say 20 students, out of which say 5 are girls and say 15 are the boys, and I am making a team of 3 persons where I am selecting randomly, then what is the probability that say there is at least a girl? Suppose I am considering say uh, persons who are infected with a particular disease. So for example, in the present times with COVID, so I consider test on say 10 people, what is the probability that say 3 will be infected and so on. So the applications of this are quite obvious, but there are even more you can say useful applications. Many times we want to estimate the size of the population. So for example, you might have already read so many things in the news. So for example, the tests are conducted on a certain number of people for COVID, and then they say that these many people are infected and these are not infected. But what is the number of people in the whole population which is infected? Because everybody may not be tested. Okay, so there are estimates. Of course, you have seen a lot of different kind of estimates in different populations and different countries. But we can see here one very simple estimate coming from the hypergeometric distribution. So suppose we have say suppose population size n is unknown. Okay, So what we are able to do is that we are able to select some people, and from that some people we are able to find out what is the number of infected people there. So for example, X is the number of infected people out of N. Now this you are saying it is an estimate of the M by N, isn't it? So here you can say M is approximately N, because expectation of X by N is M by N. So M is approximately N X by N. That is one way of looking at it. Okay. Suppose, so here if M is unknown, we are able to estimate like that. Another one is estimating N itself, that is M N by X. So different type of estimation, the total number of people of type 1, the total number of people of in the population, all of these things are possible to be estimated here. Okay. Okay, sorry, I wrote here population size. This is not population size. Suppose M, that is the type 1 items. Okay, that is unknown. Then that is estimated like this. If population size is unknown, then we estimate like this. So there are various applications of this hypergeometric distribution. I had mentioned to you that tomorrow you will have a class test during your class hour 12 to 1. I have already mentioned to you that there it will be objective type of question paper. Objective in the sense that you have to write a answer which is a number, okay, some real number which you have to write in the decimals, or usually if the probability is asked, definitely it will be in the decimals. So you have to fill in the blanks there. So it may be like accurate up to 2 decimal places or accurate up to 3 decimal places, etc. So you should have your calculator with you, because you will have to convert the number. For example, you get a fraction, say 3 by say 3 by 41. So then you have to convert that number to the fraction. So you should keep your calculator with you. Second thing is that the questions that will be given, you will not be able to navigate back. Okay, so once you finish a question, then you submit the answer for that, and then you proceed to the next question. Okay, because if we allow to and fro, then the load on the server will be too much and there will be failures. So what has been observed in maths 1, etc. also, that it is easy if we don't allow, and also it will allow not to waste your time also. The tomorrow's test is on probability only. That means your basic probability, the definitions, then whatever rules were there. So I have given you one assignment also along with its solutions. I hope all of you are able to solve those problems. So you could solve all the problems in that assignment, because
Yes,
the
sir.
solutions are given there. So I think you should not have any difficulty. So of course you can practice more also, because it is not that the problems from the assignment will be asked in the exam. In fact, problems will be similar but not the same. I mean, for example, there are problems which are based on permutations and combinations. That means selection problems, counting problems, and then there are certain problems where conditional probability or the Bayes theorem or the multiplication rule or the independence of the events, those things are used there. So problems will be based on all such things. If you have any question in general to ask, you can just ask me. Otherwise, I can proceed to the next discrete distribution in our list, because I have covered, in fact, most of the important distributions. But there is one very, very important distribution which is there, and I will need time to explain that thing. So if there are any question, then you can just ask right now. Otherwise, I will proceed to the next distribution.
Excuse me, sir.
Yes.
Sir, on what platform will tomorrow's test be conducted?
It is Moodle.
Okay, sir.
So you may be getting the link and the login password, etc. Today they will give you. Okay. The exam is during the regular class hour. So between 12 to 1, and the timing for the test is 45 minutes. Okay. So you join in time so that you don't lose any time there. I have kept little less than the 1 hour because some of you may be attending the previous class and therefore there will be a gap there. So that is why I am keeping only 45 minutes. So once you start, then you get 45 minutes from the time.
Sir,
Yes.
in the assignment 1, could you please explain the question number 14 once more?
Question number 14. Okay.
Yes.
Let me just see what is the problem here. S is the set 1 to n, this problem. What is the problem? That S is equal to 1 to n set?
Yes, sir.
Okay. Suppose A and B are independently equally likely to be any of the 2 to the power n subsets, including the null set and S itself. Let X denote the number of elements in B. Okay. So what is the probability that X is equal to I? So X is equal to I means that the number of elements in the set is I. So if I am having I elements out of n, then the number of ways of selecting that is nci. Okay. So the number of sets which have I elements is nci, and the total number of subsets are 2 to the power n. Since here I am assuming equally likely and of course independently also, I mean of course A and B are independent, but equally likely to be any of the 2 to the power n subsets, then the probability will be simply calculated using the classical definition. So it is nci divided by 2 to the power n, where I can take values 0 to n. The sum you can check actually, that nc0 plus nc1 plus ncn, the sum of the binomial coefficients is 2 to the power n. So it is 2 to the power n by 2 to the power n, that is 1. So this is all right. The next one is that what is the probability that A is a subset of B given that X equal to I. So this is then becoming conditional probability here. So what is the probability that A is a subset of B? That means in B there are certain number of elements and A is having less than or equal to that. So it will become a sum there. After summing, I have written here the answer here, but the intermediate calculations I have not written here. So that you have to work out and see what is the intermediate calculation there. In the next one, probability of A is subset of B, then you apply the theorem of total probability, that is sigma probability of A subset of B given X equal to I into probability of X is equal to I. So of course the previous two things are already calculated. So when you sum, you should get this kind of answer. Okay. So whether you are considering a subset of B or subset of B complement, it is the same thing. So it is 3 by 4 to the power n. That is the thing. I have not written the intermediate calculations, but that is for you to work out actually, because the complete set of answers I have not written in many problems. You should write the intermediate steps there.
Sir, also in total test, how many questions will we be having in the 45 minutes?
You have to answer 10 questions. You will be getting, each student will be getting 10 questions, but you will not be getting the same questions. Okay. So therefore, do not try to contact each other through WhatsApp and other kind of things. because that is just unnecessarily wasting of the time. The students will not get the same questions because it is given in the random order. I have used the probability here, okay, for because the number of questions have been given in the module, so students will be distributed randomly those questions. So the probability that you will get a common question, that probability will be very small. You already solved this problem, no, common birthday problem and all those kind of things. So already I have told the calculation of the probability. So if you interpret that, the probability of getting the same question by two students who know each other, because all of you may not be knowing each other also. So 239 students are there. In fact, the exam is conducted for all the sections together. So 939 students are there. So if you know 10 students and the probability that one of them is getting simultaneously the same problem as that probability is going to be very small. Okay, so let me then move to the next one if you have no other questions. When you are writing down the exam, then please do not panic there, because the questions are not going to be very difficult or something like that. As I mentioned to you, they are based on your basic understanding of the probability, whatever concepts we have done. That means you define the event and apply the axiomatic setup. That means multiplication rule or the addition rule or the conditional probability or the theorem of total probability or the Bayes theorem, and certain basic counting techniques that you already know, permutation, combination kind of thing, or simple counting also is possible. So all these kind of problems are there. I don't think you will have any problem in those things. Only thing is you should not panic, and for example, something as simple as that we have given you the problems like if A and B are independent, okay, then what happens? That you have that probability of A intersection B is equal to probability of A into probability of B. I have also mentioned when we were talking about independence that if A and B are independent, then A and B complement are also independent, and so on. So these kind of simple things are there. Only thing is that you just do it carefully so that you don't make a mistake, because we are not in a position to check your calculation there. We will be only able to see your answer. So because you will be filling up it in the specified place there.
And sir,
Is that okay?
is navigation is there in the questions?
No, I already mentioned to you navigation will not be there, because you will solve one problem and you will move ahead. If I allow the navigation, then the system will crash there. That has already happened in chemistry and maths in the first year classes. So we will not be in a position to do that, because when you do that, then loading, uploading, because every time you move to the question, then there is a lag of, there is a load of loading of that questions. So it will be quite complicated. The current resources that we are having here will not be able to support that.
Excuse me, sir.
Yes.
Yeah, could you please reiterate the syllabus like one final time? There's some confusion.
It is the probability portion. I have already written in the MS Team this sheet that is uploaded there. Have you not seen that?
I haven't taken a look there, sir. I'm sorry.
You are not seeing what is the material which is being uploaded, then this uploading and all will not be of much use if you don't see all those things. I am uploading all the lectures also. Are you able to see them?
Yes, sir. I've downloaded
Yes, sir.
the lectures.
Yes, sir,
I'm
we
just
can see
looking for the
that. Yes, sir.
syllabus.
Yeah, so please look at there because I am uploading assignment, I am uploading the solutions, then any instructions are there that are also being uploaded. So please see those things, otherwise it will remain incomplete kind of thing. I have written that probability is the syllabus for the first one. Okay.
Yes, sir,
All
thank
right.
you.
I think then let me move to the next topic, that is Poisson process, which basically leads to the Poisson distribution. In fact, whatever experiments I was mentioning to you till now, in that once I describe the experiment, then you are able to tell the probability without too much difficulty. For example, how do you calculate the probability mass function of a geometric distribution? You are able to tell, because if I am giving the condition, then I am asking the question, what is the probability that on the kth trial you get the first success? You are able to tell that. What is the probability that in k trials you get 4 success? You are able to tell in a binomial setup. In hypergeometric, you are able to tell that number of persons of type 2 is 3. So you are able to tell all those things. From the description of the experiment, you are able to tell. But every time such a thing is not possible. So for example, when I start the class at 8 o'clock, so I switch on usually this MS Teams thing, my meet at 7:30. So when is the time? When is the time when the first student will join? Okay, if I am asking this probability, so what is the probability that the first person will join at 7:50? Okay, what is the probability that by 7:55 50 students have joined? What is the probability that by 8 o'clock 100 students have joined? What is the probability that by 8:15 150 students have joined? Okay, if I am asking these questions, how do you answer that? Can you tell? Can anybody guess that how to answer this question?
So from previous available data.
Yeah, so but this is time here, no? So previous data you should have the equally likely number of equally likely events, and then you can consider ratios and so on. But here that is not possible.
No, sir, I was talking about previous observations in the same experiment. Like when do people join in at the class or something like that?
No, that is all right. But suppose I want to find out that you are telling about conducting the experiment repeatedly. That is a different thing. I am, because that of course you can apply in general. That is a general technique. I am asking a particular problem. Okay. So of course I don't expect an answer right now here, because it needs to be looked at in a more structured fashion. So as I mentioned that the number of students joining the class within a time frame. Okay. So the same thing you just extend to various things. So for example, you are standing at a traffic crossing where you have to cross the road, and you are observing the vehicles coming from both the directions. So how many vehicles cross you during say 1 minute period, or during 30 seconds period, or during 2 minute period? Suppose you are waiting at a say booking counter, so some sort of ticket counter, then how much time you have to wait? That means how many people are there in front of you, okay, who will take the ticket before you. So of course nowadays a lot of things have been digitized, like you are using online applications. Earlier it was like physically one has to stand in a queue. Nowadays of course you do through your system, but then system also there is a waiting time. It is not that when you click then nobody else is there. So somebody is there in before you in the queue, then he will get the priority before you. Okay. So whenever we are talking about such events, and of course there are even other kind of things. So for example, how many accidents do take place per day? Okay. So for example, how many accidents take place in a city? How many accidents do take place in a country? How many accidents do take place in a locality? Isn't it? So how many times, say, there is a hit on a server for a particular information? Okay. So these are all data that are recorded, but there can be a distribution there. Okay. So whenever we are observing the events happening over time, area or space, then if they satisfy certain kind of structure, we can calculate the distribution. So here we are saying we are observing events or say something happenings over time, area, space, etc. Okay. So suppose we say, suppose we take time. Okay. So time means it is like this. Okay. So some timeline I will make, starting from 0, we go up to a certain time t, t plus h kind of thing. Okay. We are observing events. So some event may occur here, some events may occur here, some event may occur here, and so on. Okay. These are the time bars here. We say that the occurrences are happenings they follow a Poisson process. So we say that these occurrences which are being observed over time, they are following a Poisson process provided they satisfy the certain axioms or assumptions. So what are those assumptions? The first assumption is that the number of occurrences in disjoint time intervals are independent. For example, if there is an accident today in a particular town, then it is independent of that whether there will be another accident tomorrow in the same place. Okay, so that is independent. If we are looking at the events occurring over area, then whether there is an accident, say in a city of say Kanpur, and whether there is an accident in a city of say Nagpur, they are independent. Okay. So such things can be assumed. So I was mentioning about the students joining. So a student joining my class online. So a student is joining from some place, say Patna, and then there is another student who is joining, say from Guwahati. So it is independent because they are all joining independently. So that can be assumed. Similarly, whether some students will join between 7:55 to 7:56 and some students who will join between 7:56 to 7:57, that is considered to be independent. And the second assumption is that the probability of a single occurrence during a small time interval is proportional to the length of the interval. So we put it in mathematical notations like this, that suppose I say x h is the number of occurrences in interval of length h. For example, I mentioned here, say I made this graph. So here t to t plus h, okay. So in this interval, so I take h to be small. Usually in mathematical notation, we take delta t or h for using a limit thing like h tending to 0 kind of thing. So in this interval, what is the probability that one event will occur? So I call it probability of xh is equal to 1. Then that is proportional to the length of the interval. So proportionality constant we can assume, say lambda. So lambda h. Okay. I'll give another notation here. And then the third assumption is that probability of more than one occurrence in a small time interval is negligible. So this is the third assumption. Let us say denote. So xt is the number of occurrences in an interval of length t. Okay. Then probability of xt is equal to n. We will use the notation pnt. Okay. This is a notation that we will use. Under assumptions 1 to 3, p and t is e to the power minus lambda t to the power n by n factorial. N is equal to 0, 1, 2 and so on. Let me give this name of this equation as 1. So this is basically the probability distribution of number of occurrences in a Poisson process, where we are looking at the number of occurrences during a fixed time interval. Okay. This is basically the form of the Poisson distribution, but let me not use the name at this moment. I will tell it later. So let us go back to the assumptions once again. I have used the notation P and T. P and T means one occurrence, n occurrences in the interval of length T. Okay. So If you look at the second assumption says that probability of one occurrence in an interval of length h, that is a small time interval. So we can put it as P1h. Okay, P1h is lambda h. And here I am saying probability of more than one occurrence. So more than one occurrence means it could be 2 occurrences, or it could be 3 occurrences, and so on, which we can also write as 1 minus no occurrence or 1 occurrence. And the assumption is that this is negligible. So by negligible we mean we use a mathematical notation small o of h. Those who have done programming and data structure etc., probably you are aware of this notation. So OH by H is a number something like this. See, if I say half, what is half square? Half square is less than half. Half cube is less than half square. That means progressively it will become 0. Like if I take half to the power n, it goes to 0. So by this I mean that this goes to 0 as h tends to 0. So OH is a small amount. So probability of more than one occurrence in a small time interval is negligible. Physically, if you look at it, so for example, if I am looking at say a serious natural calamity, for example, something like an earthquake. So if there is an earthquake in a particular year in a country, the probability that, say for example, a country like India, so what is the probability that there will be a second major earthquake in the same year? So the probability of that will be negligible. But if you are considering say a country like Japan, then it will not be yearly, there it is hourly, because there per day the number of earthquakes is 3. So there maybe you have to consider the occurrence in the interval of length say an hour. So now if you understood the notation OH, then here also we can have a little bit more of flexibility. In place of this I can write here lambda h plus OH also. Okay, little bit flexibility we can have by adding something. That means it is proportional, but it may not be exactly proportional also. It may be getting modified by little bit of the terms there. Okay. So these are our assumptions here. The number of occurrences in disjoint time intervals are independent. Second is the probability of single occurrence is proportional to the length of the interval. And the third one is the probability of more than one occurrence is negligible. So from here actually if you can conclude that because P1H I have put as lambda h, so P0H is equal to 1 minus lambda h plus OH. Now plus OH and minus OH is same. I mean I can put minus OH also here. It doesn't make any difference. Okay. Under these assumptions we have to prove that P and T is of this form. Okay. So in the next class then I will start the proof of this one. Of course we will use the method of induction for this one. So let me stop today's class at this point of time. And tomorrow we will have